In this lesson, we want to review factoring out the greatest common factor, which is abbreviated as the GCF. So before we kind of jump in and start looking at some sample problems where we're factoring the greatest common factor out from a polynomial, we want to first think about what is the greatest common factor for a group of monomial terms. So most of you would have learned this in either pre-algebra or kind of your first algebra class. That could be Algebra 1 or just a general algebra course. And essentially, it's a very easy procedure, just something you might have forgotten. To find the GCF for a group of monomial terms, you want to first think about the number parts, and then you can think about the variable parts. The variable part is very, very easy. The number part takes a little bit of work because you have to factor some things. So if I look at 14x squared y, 35xy, and 56x cubed y to the ninth, and we ask what is the GCF, I'd start by factoring each number. So 14 is 2 times 7, 35 is 5 times 7, and 56 is 8 times 7, and 8 is really 2 cubed. So I can write this as 2 cubed times 7, or you could write out 2 times 2 times 2 if you wanted to be technical. And all I'm looking for here, when I'm looking for the greatest common factor, go through the prime factorizations and find what's common to everything, okay? So don't get confused with the least common multiple. When you're looking for the GCF, it's got to be common to everything. So I have a 7 that's common to everything. So that's what's going to be the greatest common factor, at least for the number parts, right? If I had 14, 35, and 56, and I said, what's the greatest common factor? It would be 7. Once we got our number part worked out, we think about the variable parts. Two questions you ask yourself. Number one, is the variable present in each term? Here I have x, x, and x. Forget about the exponent for a minute. Here I have y, y, and y. So I know I can put an x here and a y here. Now, what will the exponent be on each? Well, it's going to be the smallest exponent that appears on any of the copies. So in other words, if I look at x, I have x squared, I have x to the first power, and I have x cubed. What's the smallest? It's right here, right? It's x to the first power. So this guy can stay as just x, or you can write an x to the first power for emphasis if you want. And then in terms of y, I have y to the first power, I have y to the first power, and I have y to the ninth power. Again, either of these is going to be the winner in terms of what's the smallest. So you can put a y to the first power there. Now, why does that work? Well, if you think about it, the smallest exponent is the least number of occurrences on that variable. So if I was to write this out like I do with the numbers, x squared is what? It's x times x. X to the first power is just x. And x cubed is x times x times x. So what's common to everything? This has an x, this has an x, and this has an x. That's common to everything. You can't put a second x in there because that's not common to everything. This one doesn't have it. Okay, it's got to be common to everything. So that's why you go with the smallest exponent that appears on any of the copies. Again, two questions to ask yourself. Is the variable present in each of the terms? And what is the smallest exponent on the variable? If I was to look at a different problem, and we'll see an example in a second, but let's just say we change this problem, and this guy did not have a y. Let's just mark it out. So this is gone now. If that's the case, then y would get removed from the GCF because it's not present in each one. This guy has a y, this has a y, but this one doesn't. So it's not common to everything, so it doesn't go in, okay? But that's not the situation we have, so let's change this back to what it is. So our GCF here for these three terms is going to be 7xy. All right, let's look at another example. So we have 8x to the 6th power y cubed z, 20x squared z to the 4th, and 36x cubed y to the 5th z squared. So what is the GCF, or again, the greatest common factor? So for the numbers, I'm going to factor each one. So 8 factors into 2 cubed, or 2 times 2 times 2. 20 factors into what? We know it's 4 times 5. 4 is 2 times 2. And 36, we know, is 9 times 4. So let's write 4 as 2 times 2, and then 9 is 3 times 3. Okay, what's common to everything? I've got 1, 2, I've got another 2. That's common to everything. Then I've got a third 2 here, not common to anything else. I've got a 5, not common to anything else. And I've got 2 3s here that are not common to anything else. Now, since the 2 copies of 2, in other words 4, is common to everything, That's going to be the GCF, at least for the numbers, right? For 8, 20, and 36. Now, in terms of the variable part, is the variable present in each term, and what's the smallest exponent on that variable? You have an x, an x, and an x. You have a y, no y, so y is not going in. You have a z, and a z, so z is going to go in. Now, what's the exponent on x, and what's the exponent on z? So this guy is a 6, this guy is a 2, and this guy is a 3. So the smallest exponent is a 2, so this is going to be squared. For z, I have z to the first power, z to the fourth power, and z squared. So this guy is going to be the smallest, so we just leave it as z, or you could put z to the first power for emphasis if you want. So the greatest common factor here is 4x squared z to the first power, or just z. So now that we've reviewed how to find the greatest common factor for a group of monomials, we want to think about how to factor out the GCF. So when I look at something like 6 times the quantity 4 plus 3, this is a very simple example. I just want to show you the distributive property. 6 multiplied by 4 would give me 24. So let's just write this as 6 times 4 for right now. Then plus 6 multiplied by 3 would give me 18. Now, because of the equality here, I know that I could go in reverse, right? I could pull the 6 back out from each term and set it out in front of some parentheses, and I'd have what is left here, which is 4 plus 3. This property, the distributive property, allows us to write a product as a sum, and it also allows us to write a sum as a product. Now, this might seem like a really easy example because we only have numbers involved, but let's suppose we looked at something like this, 3x plus 12. How could I write this sum, right? You have 3x added to 12 as a product. So some number multiplied by some quantity. Well, essentially what I want to do is first find the GCF. So what's the GCF for 3x and 12? Well, that's really, really easy because 3 doesn't factor. And 12 I could write as 2 times 2 times 3 or 4 times 3. So I could just write this as 3 times x like this plus 3 times 4 like this. And I can pull the 3 out because that's common. So I can write that out in front of some parentheses. So just pull this guy out. And what's left inside? I would just have the x plus the 4. Okay? Very, very easy procedure. In most cases, you're not going to take the time to kind of write things out like this. To speed up the process, what I would do, I would take 3x plus 12. I would find my GCF. I know the GCF is 3. So I would just start by writing a 3 outside of a set of parentheses. And since I'm multiplying each term here by 3, to get back to this, remember, multiplication and division are opposites, so I can just take each original term and divide it by 3 to get what I'm missing, right? So in other words, if I take 3x and divide it by 3, I get x. That should make sense to you because going backwards, 3 times x gets me back to 3x. If I want this space right here, divide 12 by 3, I get 4. Again, that should make sense because 3 times 4 gives me 12. So this is the quicker way to do this. Write your GCF outside of the parentheses, divide each original term by the GCF, by what you're pulling out, and that's going to give you each spot. All right, let's take a look at another one. So we have 6x cubed minus 12x squared plus 144x. So what is the greatest common factor here? So this one's a little bit more challenging. So let's think about 6x cubed. Let's think about, forget about the sign there, 12x squared, and let's think about 144x. So I know x is common to everything, and the smallest exponent is a 1. So the GCF, let's just put an x over here. For the number part, I have 6, which is 2 times 3. I have 12, which is what? It's 4 times 3, or 2 times 2 times 3. And I have 144, which most of you know is 12 squared, right? It's 12 times 12, or 2 times 2 times 3 times 2 times 2 times 3. So what's common to everything? It's going to be 6, right? 2 times 3, 2 times 3, 2 times 3. So the GCF here will be 6x. So what I want to do now, let me erase everything. I want to write my GCF, which is 6x, outside of some parentheses. And then I want to divide each term by 6x to get the terms that are missing in here. So I've got this one, I've got a minus, I've got a term here, and plus, I've got a term here. So 6x cubed divided by 6x would be x squared. If you have 12x squared divided by 6x, 12 divided by 6 is 2. X squared divided by x is x. And I've already accounted for the minus sign. I already put it there. Okay, so you don't need to worry about that. Then 144x divided by 6x. What is 144 divided by 6? Well, that's going to give me 24. So we factored out the greatest common factor here, and we end up with 6x times the quantity x squared minus 2x plus 24. All right, let's look at another one. So suppose we had 20xy squared minus 15x squared y minus 100xy. So again, I'm looking at 20, 15, and 100. Forget about the signs. What's the GCF? Well, to do this quickly, 20 I know is 5 times 2 times 2, but just write 5 times 4. 15 is 5 times 3. So I know at this point I can get rid of this 4, and I can get rid of this 3. Really all I'm looking for is a 5 here, and I know 100 divisible by 5. So the GCF is going to be 5, right? Because the 2 wouldn't have been common to everything, so you get rid of that. And the 3 wouldn't have been common to everything, so you can get rid of that. So it's irrelevant what the factors of this are, other than the fact that it's divisible by 5 or it has 5 as a factor. So the GCF is a 5. So the GCF is a 5. Now, when we think about the variables, we have x, x, and x. And we have first power, second power, and first power, so that can stay. Then we have y, y, and y. We have second power, first power, and first power, so that can stay. So my GCF is 5xy. So let's write that out in front of a set of parentheses. And again, to get what's inside, you're going to have 3 terms. So minus, minus. So what goes here? 20xy squared divided by 5xy. 20 divided by 5 is 4. X over x is 1. Y squared over y is y. 15x squared y over 5xy. 15 divided by 5 is 3. X squared over x is x. Y over y is 1. 100xy divided by 5xy. 100 divided by 5 is 20. X over x is 1. Y over y is 1. So we end up with 5xy multiplied by the quantity 4y minus 3x minus 20. All right, let's go ahead and wrap up our lesson by looking at how to factor out a common binomial factor. This is something we're going to use in the next review section where we're talking about factoring by grouping. So let's suppose we look at the problem. The quantity x plus 1 times the quantity x minus 5 plus the quantity x minus 5 times the quantity x minus 6. So I see that I have a common binomial, meaning 2-term polynomial, so a common binomial factor. So I can just pull that out, okay? Just like I've been doing in the other problems, I can still just pull this guy out. And what happens when I pull it out? Well, inside of parentheses, I would have what? If I pull out an x minus 5 from here, I would just have the x plus 1. So the x plus 1, and you can put that inside of parentheses if you want for now. Then plus, over here, if I pull out an x minus 5, I would have the x minus 6 there. Now, these double parentheses here cause a lot of concern for a lot of students. So if you want to make this easier on yourself, just temporarily put some brackets there. We're going to combine like terms inside of here so we can get rid of the brackets in a minute. So x plus x is 2x. 1 minus 6 is going to be negative 5. So this would be 2x minus 5. And now I could write this with some parentheses here. And so you've successfully factored this guy. You've pulled out or factored out a common binomial factor. Now it's easy to prove to yourself that this works. If I go through and FOIL this, x times 2x is 2x squared. The outer would be minus 5x. The inner would be minus 10x. So you'd have minus 5x and then minus 10x. So you combine like terms there, you'd have negative 15x or minus 15x. And then the last term is negative 5 times negative 5 is plus 25. Now if I go through here, x times x is x squared. The outer would be minus 5x. The inner would be plus 1x. And the last would be minus 5. So this guy right here in the middle would combine to be minus 4x. So I'd have x squared minus 4x minus 5. And plus, over here I would have x squared. My outer would be minus 6x. My inner would be minus 5x, so that would be minus 11x if I combine the two. And then my last would be plus 30. So what does this equal? If I'm right, it should equal this. X squared plus x squared is 2x squared. Negative 4x minus 11x is minus 15x. then negative 5 plus 30 would be plus 25. So I want you to notice that we got the same thing here as we got here. So this shows you that we can factor out a common binomial factor. We end up with the same result either way, the 2x squared minus 15x plus 25. In this lesson, we want to review factoring by grouping. So most of you know at this point how to factor using the grouping method. This is basically something we use with a 4-term polynomial. And what we're going to do is we're going to separate the 4-term polynomial into 2 groups of 2 terms each. From each group, we're going to pull out the GCF, or in some cases, the negative GCF. And then we're going to look for a common binomial factor, okay? If you have a common binomial factor, you pull that guy out, and you will have factored your 4-term polynomial using grouping. So let's start out with an easy example. This is one where we don't need to really go through different combinations. And what I mean by that is I can take the first 2 as a group and the last 2 as a group. I don't need to reorder anything. So I have 15x cubed minus 5x squared plus 6x minus 2. And if I just take the first 2 here as a group, so 15x cubed minus 5x squared, I'm going to put that inside of parentheses. So that's one group. Then plus, I have 6x minus 2, so that'll be another group. Put that inside of parentheses. And what can I pull out from 15x cubed minus 5x squared? Well, the greatest common factor there is 5x squared. So let's pull that out. And inside the parentheses, I would have what? 15x cubed divided by 5x squared is going to give me 3x. And then 5x squared divided by 5x squared is 1. So I have the minus there, so I'll put minus 1. So then plus, what can I pull out from 6x minus 2? So again, the GCF of 6x and 2 would be 2. So if I pull that out, 6x divided by 2 is 3x, and then 2 divided by 2 is 1, so minus 1. So you can see that we have this common binomial factor of 3x minus 1. We can just pull that out, okay? We can factor this out. So we would have 3x minus 1 that's been pulled out in front of a set of parentheses. Inside the parentheses, we would have what's left, which is the 5x squared. So 5x squared plus the 2, okay, plus 2. So we've factored our 4-term polynomial, 15x cubed minus 5x squared plus 6x minus 2, as the quantity 3x minus 1 times the quantity 5x squared plus 2. Okay, so pretty easy. All right, now let's take a look at a harder example. So the first thing you would notice with this, we have 18xy minus 6y squared plus 12x minus 9y cubed. Everything has a common factor to start, okay? If you look at the example we looked at before, let me go back to it. If you look at this example again, we don't have anything that's common to the 4 terms other than 1 or negative 1. If we look here, we do have a common factor of 3, right? So 18 is 3 times 6. I know you could break it down further, but just think of it as 3 times 6. 6 is 3 times 2. 12 is 3 times 4. Again, you could break it down further. 9 is 3 times 3. So before I even start, I want to pull that out. If I don't pull it out, then later on I'm going to have additional factoring. Okay, so 3 times, inside the parentheses, I'd have 6xy minus, I'd have 2y squared plus, I'd have 4x, and then minus 3y cubed. Again, I just pulled out a 3 from each term here. Okay, that's all I did. Now, inside the parentheses is where I'm going to be working. Okay? Now, if I just take these first 2 terms and these last 2 terms, I'm not going to end up with a common binomial factor. So here's where I got to kind of do some trial and error, try different combinations. Now, if I look at the GCF of 6xy and 2y squared, that's going to be 2y, right? If I pulled that out, what would I have inside? I would have a 3x minus y. Here, the GCF is 1, or you could do negative 1. But that's not going to get me anything here, right? It's not going to match up with the 3x minus y. I would have 4x minus 3y cubed, or I would have negative 4x plus 3y cubed. Either way, it doesn't work. So we're going to need to try a different arrangement here. So one thing that I notice is that this guy right here has an x, and this guy right here has an x. So that's a little hint, hint. So I'm going to arrange those terms next to each other. So don't forget my 3. So I'm going to put my 6xy and my plus 4x. That's going to be a group. And then you will have negative 2y squared and minus 3y cubed. So plus negative 2y squared, and minus 3y cubed. What I want to do is pull out the GCF from this group here. So 3 times. You have a 6xy and a 4x. I know I can pull out an x, and I know I can pull out a 2. So this would be 2x times the quantity. 6xy divided by 2x would be 3y. And then 4x divided by 2x would be 2. So plus 2. Then plus. Here, I know that I need to pull this negative out. How do I know? Because if I look at what my binomial here is, it's 3y plus 2. Everything's positive. So I would want everything in here to be positive. So go ahead and pull out a negative. So you can write a minus here, or you can put plus negative. Doesn't matter. And I'm going to be pulling out what? Well, I'm just going to be pulling out a y squared. And then inside I would have 2, right? If I pulled out a negative y squared, I would just have 2. And then plus, if I pulled out a y squared here, I would just have 3y. Now, you might say you don't have a common binomial factor. You have 3y plus 2 and you have 2 plus 3y. These are the same terms, they're just in a different order. When we can add in any order, so it's the same thing. If you wanted to, you could just reorder this stuff. You could say this is 3y plus 2. It's the same. Or you could go back here, rearrange these terms, put the negative 3y cubed in front, and then put minus 2y squared as the last one. It doesn't matter. It's the same answer either way. So put equals. So now we're going to factor this guy. So this guy is your common binomial factor. And if we pulled that out, we would have 3 times the quantity. This guy comes out, 3y plus 2, times, inside of parentheses, you'd have what's left. So you'd have the 2x minus the y squared. And that's our factorization. So you have 3 times the quantity 3y plus 2 times the quantity 2x minus y squared. Now, if you didn't pull out the 3 to start, okay, like we did, then what happens is when you get to this stage, you're going to have a common factor of 3, okay, that you still need to pull out. So always look before you start, say, is there anything I can pull out before I start factoring this by grouping? It's going to save you additional factoring in the end. All right, let's take a look at another one. So suppose we had 100xy minus 245 minus 140x plus 175y. So before we start, is there anything we can pull out? This is divisible by 5, so is this, so is this, so is this, right? Everything ends in a 0 or a 5. So I know everything's divisible by 5. This guy right here would be 5 times 20. This guy right here would be 5 times 49. This guy right here would be 5 times 28. And this guy right here would be 5 times 35. So there's nothing else I can pull out. You notice that this guy, and this guy would each have a common factor of 7, but this guy doesn't, right? 20 is just 4 times 5, so that's not going to work. And so there's nothing else we can really pull out other than a 5. So we'd write a 5 out in front. Then inside the parentheses, you'd have 20xy, minus you would have 49, minus you would have 28x, plus you would have 35y. All right, let's erase all this. Get rid of that. And we'll move this up here. Okay, so now let's think a little bit about our grouping. If I look at the way it's grouped now, in other words, these two as a group and these two as a group, the first two as a group and the last two as a group, will that work? Well, from the first two, I can't really pull anything out. 49 is 7 times 7. 20 is 5 times 2 times 2. Nothing I'm really going to be able to do there. This has x, y. This doesn't have any variables at all. This guy, I know I would have an x and I know I would have a y. And I could pull out a 7, but it's just not going to work, right? So you can eyeball that and see we've got to rearrange things. Again, I'm going to think about the fact that this term right here has an x, and this term right here has an x. So let's go ahead and rewrite this as 5 times inside of one group. I'm going to use brackets here to make this a little easier to see. So one group could be 20xy, and then minus 28x, and then plus. Another group could be 35y minus 49. All right, let me close those brackets. The reason I went ahead and switched these around, if you notice, this number part right here, this 28 is larger than this number part here, 20. So I just followed that same order. This number part here, 49, is larger than this number part, 35. Okay, so that's where I got that. All right, so now if we pull out the GCF from this first group, what will it be? 20 is 4 times 5, or 2 times 2 times 5 if you want to be technical. 28 is what? It's 4 times 7, or 2 times 2 times 7. So I could pull out a 4, and then I could also pull out an x. So inside the parentheses there, you would have 5y minus a 7. From here, I know I could pull out just a 7. Right? If you think about 35 and 49, greatest common factor is 7. So I'm going to pull that out, and inside I would have 5y minus a 7. So you can see you do have a common binomial factor. So we have this guy right here, this 5y minus 7. And let's go ahead and pull that guy out. So we'll have our 5 out in front. Then we'll have our 5y minus 7. Then inside the parentheses, we'll have 4x plus 7. Okay, so we factored our polynomial as 5 times the quantity 5y minus 7 times the quantity 4x plus 7. All right, let's go ahead and take a look at one more problem. Pretty easy concept overall, just something we need a lot of practice with. So if we have 21xy minus 112xz minus 84x squared plus 28yz, think about what's common to everything before you even start. Can I pull anything out? Variable y's, no, right? You have an x, an x, an x, no x. You have a y, no y. You don't have a z here, so nothing's going to be common there. So let's start with 21. 21 is 7 times 3. So is anything divisible by 3? Is anything divisible by 7? 112, 1 plus 1 is 2, 2 plus 2 is 4. That's not divisible by 3. So now let's think about divisibility by 7. 112 divided by 7 is 16. So I could write this as 7 times 16. 84 divided by 7 is going to be 12. So I could write this as 7 times 12. And 28 divided by 7 is 4. So this is 7 times 4. So before I even start, I can pull out a 7. And inside I'd have 3xy minus I would have 16xz minus I would have 12x squared. And then plus I would have 4yz. Now, is this the correct order? Meaning, can I get a common binomial factor? So just eyeballing this, you can see that using the first two as a group and the last two as a group will not work. And the reason I can tell that so quickly is this guy is x squared. Over here, I'd be pulling out an x, and I wouldn't have an x anywhere inside of the parentheses, right? Here, I'd be stuck with that x squared, right? There's no x over here to pull out anything. So knowing that, I'm going to have to reorder. I would look at the fact that you have a z here in this term, and you have a z here in this term, right? If I pulled out the z, I would be left with variable y's x and then y. If these two terms were next to each other, if I pulled out an x, I would be left with x and y. So the variables work themselves out. So let's try that guy, okay? So you just need to get some practice kind of going through different combinations, and you'll become very, very good at eyeballing these things and getting the correct order. So my 7 goes out in front. I'm going to put negative 16xz plus 4yz. And then I'm going to put negative 12x squared and then plus 3xy. And again, the reason I put them in this order is because the negative 16 is larger than the 4 in terms of absolute value. I know negative 16 is a smaller number, but in terms of absolute value. And then the negative 12 in terms of absolute value is bigger than the 3. So that's why I chose that order. All right, so let's go down a little bit and get some room. From the first group here, I can pull out a negative 4z. Okay, so negative 4z. So this first term would be positive. It would be 4 and then just x. The second term would be negative, right? Because if I divided this by this negative, I would end up with a negative. So I'm pulling out a 4, I'm pulling out a z, I'm just left with a y. All right. Over here, I can pull out a negative 3x. Okay, pull out a negative 3x. And I'm going to be left with inside, if I take this guy divided by this guy, I'm going to end up with a 4x. And of course, this guy divided by this guy would give me a negative y. Okay, so close the parentheses there. And so we do have a common binomial factor of 4x minus y. And if we factor that guy out, just like we've been doing, we'll have 7 times, we'd have 4x minus y. And then times what's left. You have negative 4z and then minus 3x. Now, To make this look a little bit cleaner, it's not necessary, this is the correct answer. A lot of people will tell you to make your leading coefficient for any polynomial, it could be a binomial, trinomial, whatever it is, positive. So we could factor out a -1 here. And to do that, I'm just pulling the negative out from here and here and just sending it out here. Okay, so I'm just sending it out. And let me kind of make those arrows a little better. So let me be more accurate. So this guy would come out here and this guy would come out here. So we can say this is equal to, I'd put a -7, because -1 times 7 is just -7, times the quantity 4x minus y. I pulled the negative out from each, so it would be 4z plus 3x inside. And so this would be a kind of better answer, you would say. But if you wrote this on a test, it wouldn't be wrong. There would be nothing wrong with it. But a lot of online calculators, a lot of textbooks would make the extra step and write it like this. So -7 times the quantity 4x minus y times the quantity 4z plus 3x. In this lesson, we want to review factoring trinomials when the leading coefficient is 1. So anybody that's ever taken an algebra course will have run across the topic where they deal with factoring trinomials into the product of two binomials. Okay, it's very, very common. So the easier scenario occurs when the leading coefficient is 1. So in other words, if we look at a trinomial, which again is a 3-term polynomial, like ax squared plus bx plus c, and this is just something generic, something you'd see in your textbook. If we let a be equal to 1, okay, if we let a be equal to 1, I'm saying that I have a coefficient of 1 on that leading term. So I'd have 1x squared plus bx plus c, which really 1 times anything is itself, so I could just write it as x squared plus bx plus c. This is the easiest case scenario, okay? And the reason for that is, if I'm going to write this as the product of two binomials, remember when we multiply binomials together using FOIL, it's first times first, right? First terms. That's the f in FOIL. So how do I get x squared? It's just x times x. I don't need to figure that out. That's already figured out for me. I just need to figure out this spot and this spot, okay? So that eliminates a lot of the work that you're going to come across when you deal with something where the leading coefficient is not a 1, right? If you had something like 5x squared as your leading term, or if you had something like -27x squared as your leading term, something like that. So let's start out by looking at the product of two binomials using the FOIL process, and then we're going to kind of reverse it and see how we can go back to this. So we're going to go from this to a trinomial, and then from the trinomial back to this form. So doing FOIL, we start with the first term. So x times x is x squared. So again, this is a given. When you have 1x squared or just x squared, when you go backwards, you know you're going to have x and x, right? So the first terms in each polynomial are a given. Then the outer, you have x times 10, which is just plus 10x. The inner, you have 1 times x, which is plus 1x. And the last is 1 times 10, which is just plus 10. So we combine like terms here. We have 10x plus 1x. So we're going to end up with x squared plus 11x plus 10. Okay, so if I was given this and I was told to go back to this format, what would I do? Well, I know that I would start with x and x. That's pretty easy, right? X times x gives me x squared, right? How would I get this spot here and this spot here? Well, let's think about it. We know that we multiplied the outer terms, x times 10 to get 10x, and the inner terms, 1 times x to get 1x. We know those combine to give us 11x. So in other words, this coefficient here of 10 plus this coefficient here of 1 added together to give me this coefficient here that's on my middle term. So 10 plus 1 gave me 11. So 10 plus 1 gave me 11. Then notice that the same two integers, 1 and 10, multiplied together to give me this last term here. So 1 times 10 is equal to 10. So that tells me that what I need to find for these two spots here are two integers that sum to 11, or this middle coefficient here, and that have a product of the last term there. So two integers, again, let me repeat, two integers whose sum is the coefficient of the middle term, okay? The coefficient for the variable raised to the first power, and whose product is going to be the constant term. So give me two integers that fit that criteria. If you didn't know this, you would think about the last term here, which is 10, and you would think about the possibilities. Now, of course, you could do negative times negative here, but because all the signs are positive, I would just think about positive numbers. So 10 can be found by 1 times 10, or you could also do 2 times 5, okay? 2 times 5 won't work because 2 plus 5 is 7. 7 does not equal 11, right? We need something that sums to 11. But 1 and 10 does. 1 plus 10 gives me 11. 1 times 10 gives me 10. So I know I would need plus 1 here and plus 10 here, okay? So pretty easy. The first time you hear it, it might not make sense. It might not all register. But as we work through a few examples here, you're going to be like, oh, this is a very, very easy process. All right, let's take a look at another one. So we have x squared plus 3x minus 28. Again, very easy to factor this. I'm just looking for this right here and this right here. This guy right here is a given. This is going to be x and x. I don't need to worry about that. This guy right here, this last term, is a negative 28. So because it's a negative, it can only be produced from a positive times a negative. So I know I have different signs. So to remind myself of that, I might as well just say a plus and a minus, okay? Because I'm going to have alternating signs. And the order here doesn't matter, right? I could put the plus here, the minus here, doesn't matter, okay? So let's just think about positive 28. We'll work out the signs in a minute. And I want to think about how I can multiply two numbers together to get 28. So what could I do? I could do 1 and 28. I could do 2 and 14. I could do 4 and 7. And that's basically it. So now I want to think about two numbers here that would give me this middle term of plus 3. So that tells me that the bigger number is going to be positive. So if I did 28 minus 1, that would be 27. That's not 3, so that's not going to work. So you can take this out. Then if I did 14 minus 2, that would give me 12, so that doesn't work. If I did 7 minus 4, that's 3, so that's going to be my big winner. So I know that I would need a negative 4 and a positive 7. Again, the way I know that is, if this is plus 3, that's only going to come from a positive 7 minus a 4, or a positive 7 plus a negative 4. So that's why I have a minus 4 and a plus 7. Now to check this, we can FOIL. X times x is x squared. The outer would be minus 4x. The inner would be plus 7x. And the last would be minus 28. Combined like terms here, you'd have plus 3x. So you'd have x squared plus 3x minus 28, which is, again, is what we started with right here. Okay, so we know we have the correct factorization. All right, let's take a look at another one. So we have 5x squared plus 10x minus 15. You might see this problem and say, whoa, we're supposed to be dealing with easy ones. What's going on with this 5 in front of the x squared? Well, relax for a minute. You might want to look at every term here and see, can I pull something out? Always, always, always when you're factoring, as a rule, before you do anything, ask yourself the question, is there something that I can pull out from each term other than a 1 or a negative 1? Because that's going to save you from additional factoring later on, okay? So I notice that everything here is divisible by 5. If I pull that out, inside the parentheses, I would have x squared plus 2x minus 3. And now I just need to factor this part, okay? So I'd have 5, and then inside the parentheses, I know this would be an x, and this would be an x. And then give me two integers whose sum is 2, and whose product is negative 3. 3 is a prime number. I can only get 3 from 1 times 3. So it's a question of, can I arrange this in such a way that I get a positive 2 as a sum and a negative 3 as a product? Well, yes, I can. I can do plus 3 and minus 1, right? Because if I take positive 3 and I subtract away 1, I get 2. If I take positive 3 and I multiply by negative 1, I get negative 3, right? And if you want to check this, first you would multiply your two binomials together. So x times x is x squared. The outer would be negative x. The inner would be 3x. Sum those together, you get 2x. And the last would be minus 3. Now we need to multiply this by 5 to get back to our original. 5 times x squared is 5x squared. 5 times 2x is plus 10x. And then 5 times negative 3 is minus 15. So this matches this exactly. 5x squared plus 10x minus 15. 5x squared plus 10x minus 15. All right, for the last problem, we're going to look at one that kind of trips students up a little bit. So we have 6x squared minus 90xy plus 324y squared. So the reason this is a little bit more complicated is because it has two variables involved. But really, if you just kind of follow the simple technique that I'm going to show you here, it's not going to be any harder, okay? So start out by, again, asking the question, can I pull anything out? Well, yeah, I can pull out a 6. This is divisible by 6. 90 is divisible by 6. 324 is divisible by 6. This is 6 times 15. This is 6 times 54, okay? I can't pull any variables out because I have an x here and an x here, but no x here. I don't have a y here, but I have a y here and here, so nothing that's common to everything. So if I pull out the 6, I would have x squared minus 15xy plus 54y squared. Okay, so erase this, and I'll kind of scooch this up just a little bit. Bring that up there. All right, so I'm looking to factor what's inside. So I'm going to set up my two binomials. So I'm just going to put x here and x here. Now, in terms of the y, think about this last term for a minute. We end up with y squared here. How do you get y squared as a product? Because remember, this has to come from this times this. It has to be y times y. So go ahead and just write y and then forget about it, okay? You don't need to think about it again. If they give you this two variable scenario, that's all you need to do. Take the thing that's squared here and again, figure out y times y will give me y squared. If it was z squared, it would be z times z. If it was q squared, it would be q times q, so on and so forth. I only now need to think about the negative 15 and the 54, okay? So give me two integers that sum to negative 15 and that give me a product of positive 54. I know that has to be a negative and another negative, okay? Two negatives sum to be a negative, and two negatives multiply to give me a positive. Okay, so that's how I know that. So thinking about factors of 54, I've got 1 times 54. I've got 2 times 27. None of these would work. I've got 3 times 18, and that still wouldn't work. But then I come across 6 times 9. So 6 times 9 is 54. Now, again, I want negative 6 and negative 9. So negative 6 times negative 9 is positive 54. And negative 6 plus negative 9 is going to give me negative 15. So that's what I want. I want a negative 6 and a negative 9. So I've got my minus 6 here and my minus 9 there. And that's it. Okay. You can go through and check this with FOIL. Very easy to do. And I would just put my 6 out in front. X times x is x squared. The outer would be minus 9xy. The inner would be minus 6xy. So if we combine like terms here, we have x and x, both raised to the first power, y and y, both raised to the first power. So you just want to do negative 9 minus 6, which is negative 15. So minus 15 times xy. And then the last, we have negative 6y times negative 9y. That's plus 54. Again, y times y is y squared. Okay? So very easy to do. And if we want to finish this process, 6 times x squared is 6x squared. 6 times negative 15xy is minus 90xy. And then finally, 6 times 54 is 324. And then times y squared. So again, we end up with exactly what we started with. If we factor this guy, we end up with 6 times the quantity x minus 6y times the quantity x minus 9y. In this lesson, we want to review factoring trinomials using the AC method. So in the last review session, we talked about the simplest case scenario for factoring a trinomial. So that occurs when you have something like ax squared plus bx plus c, and a is equal to 1. So if I had something like x squared plus, let's say, 5x plus 6, we can very easily factor this. We know the first position of each binomial is going to be x, because x times x, the f in FOIL, would give me x squared back. To find this and this, I only need to figure out two integers whose sum is the coefficient of the middle term, so whose sum is 5, and whose product is the final term or the constant term. So give me two integers whose sum is 5 and whose product is 6. Well, I would say 2 and 3, right? 2 plus 3 is 5. 2 times 3 is 6. So this would factor into x plus 2 and times x plus 3. So very, very easy, very simple stuff. In the case where we get something where we can't factor it, we consider it to be prime. So you might see something like x squared plus 4x plus 7. If you're asked to factor this, well, when you start the process, this is x and this is x. Give me two integers whose sum is 4 and whose product is 7. Well, it doesn't exist, right? So you think about 7 as 7 times 1. It's a prime number. There's nothing else you can do. So 7 plus 1 is 8. That doesn't get me to 4. So when you get something like that, you can just stop and say that it's a prime polynomial. It cannot be factored using rational numbers. Now, what we're going to talk about today is the more complex scenario, the scenario that most students hate. And the reason students hate it is because it ends up being a lot more work, right? It's just very, very tedious. So if we have a trinomial such as ax squared plus bx plus c, now a is not going to be equal to 1. So the first part of each binomial is no longer a given because this guy right here is not a 1, okay? So in order to use the AC method, sometimes people refer to it as the grouping method because you end up doing factoring by grouping. We need to understand what A, B, and C represent in a trinomial. So A is always used as the coefficient for the squared variable, so that's why you see ax squared. B is used as the coefficient for the variable raised to the first power, and then C is your constant term. All right, so let's jump in and look at a problem, and I'm just going to walk you through the process. It's not difficult, it's just something you need to write down and kind of go step by step through. So the very first thing you're going to do, if we have something like 7x squared plus 51x plus 14, you want to identify, again, A, B, and C. So A is the coefficient of the squared variable, B is the coefficient for the variable raised to the first power, and C is going to be your constant term. Now, the very first thing you want to do here is you want to find two integers whose product is A times C. So the product of these two integers is A times C. And then the sum is going to be B, okay? So what is A times C? It's 7 times 14, which is going to be 98. So let me just write 98 here. And the sum is 51. So what you need to do is you need to go through the possibilities. You need to go through the factors of 98. So the pairs of numbers that combine through multiplication to give you 98, and see, are there two such integers that would give me a sum of 51 and multiply together to give me 98, okay? So you can start with 1 and 98. That's obviously not going to work, but just for completeness, let's do 1 times 98. So 1 and 98 would not work as a sum, right? Everything's positive here, so we're looking at two positive numbers. 1 plus 98 is 99. You can throw that out. The next thing you will come across is 2 and 49. So 2 times 49 would give me 98, and 2 plus 49 would in fact give me 51. So we can stop here. We've found our two integers. So the integers we're looking for are 2 and 49, okay? So let's erase all of this. All right, so some of you might incorrectly assume that these two integers are used like we did in the last method. I see students all the time get the two integers and go, okay, it's x plus 2 times x plus 49, okay? That's wrong. The two integers are used to expand the middle term, okay? So we're going to expand the middle term such that we have a 4-term polynomial, and we can use factoring by grouping. So in other words, what I'm going to do is I'm going to write this as 7x squared plus 49x, then plus, I'm going to do 2x, then plus 14. Now, in case you lost me there, think about the fact that 49x plus 2x gives you 51x. I didn't do anything illegal, okay? All I did was I took the middle term and I rewrote it using these two integers that we found. And so now we have a 4-term polynomial, right? We have 7x squared plus 49x plus 2x plus 14. It's the same value, it's the same thing. We're just doing this so that we can use factoring by grouping. All right, so now we want to factor by grouping. So I'm going to make this first two into a group and the last two into a group. So from the first two, I can clearly pull out a 7x. So inside the parentheses, I would have x plus 7. From the second group, I can pull out a 2. And inside the parentheses, I would have x plus 7. So if I factor out my common binomial factor here of x plus 7, I'm going to end up with an answer of x plus 7 times, we'll have 7x plus 2. So that is the correct factorization of this guy, this 7x squared plus 51x plus 14. And of course, we're just going to check it. We don't need to check every one, but I'm going to check this one just so you can see. So first terms, x times 7x would give me 7x squared. The outer, x times 2 would be 2x. The inner, 7 times 7x would be 49x. So 2x plus 49x would give you that middle term of 51x. And then 7 times 2 would give you 14. Okay, so we can see this works itself out. Again, our answer is the quantity x plus 7 times the quantity 7x plus 2. All right, so hopefully you're not too lost. We're going to try another one. We're going to do the same process. Again, just identify what's A, B, and C. So this is A, this is B, this is C, right? A is the coefficient for the squared variable. In this case, it's 6. B is the coefficient for the variable raised to the first power. Here it's 41. C is your constant term. So I want to find two integers whose product is A times C. So product is, again, A times C. In this case, that's 6 times 63, which is 378. And we want a sum of 41, right? A sum of B or 41. So obviously, 1 times 378 would not work. If we divided 378 by 2, we get 189. So you'd have 189 and 2. That wouldn't work. 378 divided by 3 is 126. That wouldn't work. 378 divided by 6 is 63. Wouldn't work. 378 divided by 7 is 54. That wouldn't work. 378 divided by 9 is 42. That also wouldn't work. So then we go to 378 divided by 14, and we get an answer of 27. Now 27 plus 14 is 41. So we found our two integers, right? We want 27 and 14. 27 times 14, again, would give me 378. 27 plus 14 would give me 41. So let's drag these numbers over here. So again, what am I going to do with these numbers? I'm going to use them to expand this middle term. That's all I'm doing. Very simple process. So we have 6x squared plus, I'm going to go ahead and write 27x first, and then plus 14x, and then plus 63. Okay? So nothing illegal here. I just rewrote the middle term. I expanded it so we can now use factoring by grouping. So let's erase this. We don't need that information anymore. From the first group, I can pull out a 3x. So I pull out a 3x. Inside the parentheses, I would have 2x plus 9. In the second group, I could pull out a 7. Inside the parentheses, I would have 2x plus 9. And I have a common binomial factor of 2x plus 9. Okay, everybody can see that. So if we factor this, we're going to have a 2x plus 9. This quantity multiplied by 3x plus 7. So this is our factorization. We get 2x plus 9, that quantity multiplied by the quantity 3x plus 7. All right, let's take a look at one that has two variables involved. So we have 30x squared minus 39xy minus 27y squared. And again, we're going to approach the problem the same way, even though it has two variables. It's very, very easy. The first thing you would notice here is that everything is divisible by 3, right? 30 is divisible by 3, 39 is divisible by 3, and 27 is divisible by 3. So I can pull the 3 out, right, before we even start. So this would be 10x squared minus 13xy minus 9y squared. So just proceed as you normally would. Inside the parentheses here, again, this is still going to be considered A. This is my B. This is my C. So give me two integers whose product is 10 times negative 9 or negative 90. So that's the product. And then for a sum, I want negative 13. So that's my sum. So running through the factors of just 90, you've got 1 times 90, which is 90. That wouldn't work, right? You've got 2 times 45. That wouldn't work. You've got 3 times 30. That wouldn't work. Not divisible by 4. But 90 divided by 5 is 18. Now you can make 5 and 18 work if you play with the signs. If you have a negative 18 and a positive 5. Right? If you have a negative 18 and a positive 5. Negative 18 plus 5 is negative 13. Negative 18 times 5 is negative 90. So those are the two integers we're looking for. So let's use that to rewrite the middle term. So we're going to have 3 times the quantity 10x squared. I'm going to put minus 18xy plus 5xy and then minus 9y squared. So you can see this y variable didn't really change anything for us. You use the same technique, the same strategy, okay? So now I'm just going to factor using grouping. So I have 3, and then inside of parentheses, the first group I can pull out a 2x. that would leave me with 5x minus 9y. From the second group, I can pull out a y. That would leave me with 5x minus 9y. So you have a common binomial factor of 5x minus 9y. And if we pull that guy out, you would have 3 times. You'd have your 5x minus 9y. And then you would have your 2x plus your y. Okay? So this guy factors into 3 times the quantity 5x minus 9y times the quantity 2x plus y. So again, it didn't really affect anything for us to have a second variable involved. It's the same process. Don't get scared if you see 2 variables. It's very, very simple to work with. It doesn't change anything. The only difference is you have a y here and a y here, right? Because y times y gives you that y squared part, okay? So let's look at one more. And for this one, I gave you one that's a bit tricky. So we have 8x squared minus 5x plus 35. Nothing you can pull out to start, so let's just look at what we need. We need 2 integers whose product is 8 times 35, which is 280, and whose sum is negative 5. So this is my product, and this is my sum, right? Negative 5. So if we think about 280, let's just go ahead and factor it. And I purposely picked big numbers so you get some practice with some things that are, kind of difficult, kind of tedious. Because a lot of times you're doing these practice problems and they're all small numbers and it takes you seconds to find the answer, right? I want something that's going to take you a little bit of time. So 280 is what? It's 28 times 10. 10 is 5 times 2. 28 is 4 times 7. 4 is 2 times 2. Okay? So we can have 1 times 280. We can have 2 times 140. We can have 4 times 70. We can have 5 times 56. We can have 7 times 40. We can have 8 times 35. You can obviously have 10 times 28. You can have 14 times 20. And that's pretty much going to be it. Now, what you're looking for here, if the product is 280, positive 280, you would need 2 integers that both were negative, right? Because you have a negative sum. So 2 negatives would make a positive in terms of being multiplied together, and 2 negatives, if they were added together, would give you a negative sum. So that's what you would need. But if you look through this list here, nothing would work, right? So sometimes you get an example where it's prime, and it takes more time because you have to go through all the factors, right, all the pairs, and see, does anything work? Well, this wouldn't work, 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 wouldn't work, wouldn't work, wouldn't work. So we can go ahead and just say this is a prime polynomial. In this lesson, we want to review factoring trinomials using reverse FOIL. So for the last 2 lessons, we've been talking about factoring trinomials into the product of 2 binomials. There's a lot of different methods out there to do this. This is one of those things that's pretty tedious. But over the years, it's gotten a lot better with the use of computers. It used to be that you would punch this in on your TI-83 or TI-89 or whatever graphing calculator you had, and that would factor it for you if you didn't feel like factoring it. Now you can type this into a variety of online calculators, and it calculates it for you in a second, okay? But you still need to understand the process that you can use to do this, because you might be asked to do this on a test for whatever reason, and you might not be allowed to use a calculator to do it. So if we look at kind of the harder scenario where we have ax squared plus bx plus c, and a is not equal to 1. So in other words, this leading coefficient, the coefficient for x squared, is not 1. If we look at an example where it's kind of easier, where a is 1, let's say we had x squared minus 2x minus 3. We can factor this so quickly because we know this guy, because it's a 1 here, 1x squared is only going to be x times x here. This is the first, or the f in FOIL, okay? So all I really need to work out is this here and this here. That's really easy. All I have to do is get 2 integers that give me a product of negative 3 and a sum of negative 2. So for negative 3, it's either positive 1 and negative 3 or negative 1 and positive 3. Well, in this case, because I want a negative sum, I want a negative 3 and a positive 1. Right? My outer would be negative 3x, my inner would be plus x. That would give me a sum of negative 2x. And of course, 1 times negative 3 is negative 3. So again, that's the easier scenario. And when we get to the more challenging scenario where a is not equal to 1, something like this guy, 7x squared minus 64x plus 9, we learned in the last lesson that we could factor this using something known as the AC method, or a lot of people might call it using a grouping method, right? Normally we use factoring by grouping with a 4-term polynomial. So with this method, essentially we gather some information and we rewrite the polynomial in such a way that it's a 4-term polynomial and we can use grouping. So really quickly, let's just review that real fast and then we'll jump into the reverse FOIL. So to do this AC method, we want to find two integers that have a product of a times c and a sum of b. So in case you don't know, we label this guy right here, the coefficient of the squared variable, as a. We label this guy right here, the coefficient of the first degree variable, as a b. And then we label this guy right here, the constant, as a c. So what is a times c? It's 7 times 9, that's 63. So that's what we want for a product. And then b is going to be negative 64. So this one's really easy to figure out. If you want a sum of negative 64 and a product of positive 63, your two integers would be negative 63 and negative 1. So what I'm going to do, I'm just going to write those two integers real quick. So you have negative 63 and negative 1. You use these two integers to rewrite this middle term. So you would have 7x squared minus 63x minus x plus 9. Haven't done anything illegal. I just rewrote the middle term, negative 64x, as negative 63x minus x. All I did was expand it, okay? So now that it's a 4-term polynomial, we can use grouping, right? So from the first group, the first two terms, I can pull out a 7x, and I would have x minus 9. From this group, I'm going to pull out a negative 1, and I would have x minus 9. So you can see you have a common binomial factor here of x minus 9. And you go ahead and pull that out. You would have x minus 9, and then multiplied by, you'd have 7x, and then minus 1. So kind of a fast method in a lot of cases, depending on how many different factors you need to go through. So some of these things, when you're factoring, you get it right away. Other things, you're there for 10 minutes trying to go through all these different possibilities, and it's just very, very tedious. So it's just the luck of the draw, right? So this method is preferred by most students because with the trial and error method, it tends to get pretty tedious depending on what you get. So let's erase this. And let's go through and talk about factoring with reverse FOIL, or again, trial and error, as some people will say. So the first thing I'm going to do is just write my parentheses here. And I'm going to think about what's going to go here and here. Now, in this case, we're lucky because we have a prime number as the leading coefficient. So this is the easiest case when you're doing reverse FOIL because I know that 7 can only come from 7 times 1. I know that x squared can only come from x times x. So I can go ahead and just put a 7x and an x, okay? If I had a 3x squared, I could put a 3x and an x. If I had a 5x squared, I could put a 5x and an x, right? So on and so forth. But if I had something that was not prime, like a 10, well then I could have 10 and 1, or I could have 2 and 5, right? So it becomes more problematic because you've got more things to check. Now, I still need to work out this and this. So how would I do that? Well, I'm going to look at this last term here, and I'm going to say, okay, what are the factors of 9? Because it's got to be that this guy right here multiplied by this guy right here gives me a product of 9. And it's got to be plus 9. Now, this guy is negative, which tells me that I need a negative here and a negative there. So factors of 9, forget about the signs. You've got 1 and 9 and 3 and 3. It's the only possibilities. So now you would go through and work out the outer and inner, right, those steps in FOIL, and see which one, or which combination more specifically, gives you the correct middle term of negative 64x. So in other words, this would be your outer and this would be your inner. So 7x times something plus x times something should be equal to negative 64x. So you can try 1 and 9, and remember we're going to want negatives here. So I'm going to put a negative 1 and a negative 9. Let's check that. So 7x times negative 1 is negative 7x, and then x times negative 9 is going to be negative 9x. If I sum those two together, I would get a negative 16x, and that is not negative 64x, so that doesn't work. Now, I need to flip these around. I need to try -9 and also -1. 7x times -9 is going to be -63x. X times -1 is going to be -x. Now, if we sum these two together, we do get -64x. So this is the correct combination. Well, remember, 7x is multiplying -9. So 7x is multiplying -9. So it's got to be x minus 9 like that. And x is multiplying -1, so x is going to be multiplying this. So this is going to be a -1 there. Okay? You can always check your result with FOIL. So we can go back and say, okay, we know 7x times x is 7x squared. The outer here would be -63x. The inner here would be minus x, so that would combine to give me a -64x, so we're good to go there. And then -1 times -9 is +9. All right, let's take a look at another one. So we have 3x squared plus 29x plus 56. So another case where we have a prime number as the leading coefficient. So 3x squared can only come from 3x times x. So I'm going to go ahead and start this off by putting a 3x and an x. And now I just need to work out this guy and this guy. And remember, this times this has to give me this. So I just think about the factors of 56. And this is positive and this is positive. So I know these are each going to be plus. Okay. So for 56, I've got 1 and 56. I've got 2 and 28. I've got 4 and 14. And I've got 7 and 8. Okay. So this is where it gets pretty tedious because you've got to go through all these combinations and say, okay, if I put a 56 here and a 1 here, does that work? Well, I've got to check the outer and the inner. So 3 times 56 is 168, so no way that's too big. If you put 56 over here, it would still be too big. So 1 and 56 will not work. You can get rid of that. Next, you've got 2 and 28. So if I put a 2 here and a 28 here, 3 times 28 would be too big. If I flip that around and put a 28 here and a 2 here, even though 28 times x is only 28x, the 3x times 2 would be 6x, and if you add those two together, it's larger than 29x, so we can get rid of that guy. So now we've got 4 and 14. So if I put a 4 here and a 14 here, that's going to be too big, right? 3 times 14 is 42, too big, right? You'd have 42x plus 4x, which is 46x, not going to work. If I flipped it around and I put 14 here and 4 here, you would have 12x plus 14x, right? The outer would be 12x, the inner would be 14x, but that's too small, right? 12 plus 14 is 26. So that would be 26x. You need 29x, so that doesn't work. So now we're down to our last possibility, which is 7 and 8. So if no combination works with 7 and 8, you can go ahead and say this guy is prime. So I'll start with a 7 here and an 8 here. So the outer would be 24x, and the inner would be 7x, so that's too big. So now let's flip it around and put a 7 here and an 8 here, and that's just right? So 3x times 7 would be 21x. The inner 8 times x would be plus 8x. 21x plus 8x is 29x, so that's what we're looking for, okay? So you can see how tedious that was. We had to go through every single possibility until we finally got the one that worked. All right, let's go ahead and take a look at another one. So we have 40x squared plus 92x plus 48. And the first thing you would notice about this problem is that every number here, the 40, the 92, and the 48, are even numbers, right? So we know we could pull something out before we start. We know we could at least pull out a 2. Now, if we went through and factored the numbers, we would find that we could factor out a 4 from this whole thing, right? So the GCF of 40x squared, 92x, and 48 would be a 4. And if I went ahead and just pulled that out now, I'd have a 10x squared plus a 23x plus a 12 inside my parentheses. So you always want to pull out stuff that you can, right? If you have something other than 1 that's the greatest common factor of your terms, pull it out. It's going to save you additional factoring in the end. So now all I want to do is work on this 10x squared plus 23x plus 12. And I'm just going to write a 4 out here. And then I'm going to set up my binomials. Now, I'm going to have 2 different scenarios, okay? And let me explain why. We have a leading coefficient here of 10, right? 10 is the coefficient for my x squared. 10 is not a prime number. So this is a somewhat more tedious scenario because I can have 10x squared coming from 10x times x, or I can have 10x squared coming from 5x times 2x, okay? either of these is possible, right? 10x times x is 10x squared. 5x times 2x is also 10x squared. So we just have to go through and kind of slug it out. We think about the fact that all the signs are positive. So I know this is plus, and this is plus, and this is plus, and this is plus. So I just need to figure out these two final terms and see which one of these is going to work out. So if I look at my 12 here, I know 12 has factors of 1 and 12. You could do 2 and 6, and then you could do 3 and 4. So let's go ahead and start with this top one, and let's think about 1 and 12. So if I went ahead and put a 1 here and a 12 here, will that give me the correct middle term of 23x? Well, the outer would be 120x, and the inner would be 1x. So we know that's too large, right? So that we can just throw that out. Now, this part right here is important, so you need to pay close attention. Can I put a 12 here and a 1 here? No, it's not possible. So the reason it's not possible is if the original trinomial you're trying to factor does not have a common factor of 2 in this case, then none of the binomials will have one. And you might say, well, we did have a common factor. We had a common factor of 4. But we've already pulled that out. That's outside of the parentheses now. Inside where we have 10x squared plus 23x plus 12, there is no common factor other than 1. Okay, so we can't pull anything else out. So this guy is not a possibility because between 10x and 12, I could pull out a 2, right? There's a common factor of 2 there. So this is not a possibility. So you can go ahead and scratch that off the list. So the next thing you would try is 2 and 6, but for the same reason that I just listed, it's not possible. If you put a 2 here, you got a common factor of 2. If you put a 6 here, you've got a common factor of 2. So you can go ahead and cross that off the list. So you really just need to try 3 and 4. You can't put a 4 here because you'd have a common factor of 2. So the only possibility left is a 3 here and a 4 here. So the outer would be 40x, and you know this is going to be too large now because the inner is plus 3x. Right? So that would give me 43x, and I'm looking for 23x. So this scenario here where 10x and x are your kind of first terms for each binomial, not possible. So you can go ahead and eliminate that, and we're only going to be working with this scenario here now. And let's kind of scooch this up, and I'll go ahead and put equals now. So is it 1 and 12? So I can't put a 12 here, again, for the same reason I have a common factor of 2. So it would have to be a 1 here and a 12 here. Does that work? The outer would be 5x. The inner would be 24x. That's going to be too large. It's 29x, so that doesn't work. So I can go ahead and eliminate 1 and 12. I'll just erase it because I don't have anything else to check with it. So now I'm going to go with 2 and 6, and that's not possible at all. If I put a 2 here, I have a common factor of 2. If I put a 6 here, I have a common factor of 2. So not possible. 3 and 4. I can't put a 4 here, so it has to be true that this is a 3 and this is a 4. No other combination is possible. So if this does not work, we have a prime polynomial. So my outer here would be what? It would be 15x. My inner would be 8x. And it just so happens that 15x plus 8x does give me 23x. So we have correctly factored this guy as 4 times the quantity, 5x plus 4 times the quantity 2x plus 3. And of course you can check this. Forget about the 4 out here. Just go ahead and do FOIL first. So 5x times 2x is going to give me the 10x squared. The outer, again, would be 15x. The inner would be 8x. So 15x plus 8x does give you the 23x in the middle. And then 4 times 3 does give you the 12. So you'd have the 4 outside of parentheses just like you have here. If you multiplied 4 by each term here, you'd get back to the 40x squared plus 92x plus 48. All right, let's take a look at one with 2 variables involved. And if you've watched the last 2 review sessions, you know this is no more difficult. So the first thing we should notice here, for 45x squared minus 230xy plus 25y squared, is we have a common factor of 5, right? This ends in a 5, this ends in a 0, and this ends in a 5. So if I pull out a 5, I would have 9x squared minus 46xy plus 5y squared. And again, now I just want to factor this on the inside. So let's put a 5 out in front. What are the possibilities? I've got a 9x squared. So it's going to be 9x times x, or it's going to be 3x times 3x, right? It's got to be one of those two because 9 is either 1 times 9 or 3 times 3. Okay, that's all there is. So when we think about this second variable, the fact that it's y squared here and a y here means I just have a y here and a y here, okay? There's nothing to worry about when you have a variable involved like a y squared or a z squared, some second variable that they've thrown in. Just look at where it is. In this position, you have a y squared that can only come from y times y, okay? So just throw it in there and just forget about it. Now we're just looking at the numbers as if it didn't exist. So I also notice that I have a negative middle term and a positive final term. So that tells me these two signs are negative. So now that I've got all that stuff worked out, what are the factors of 5? Well, it's just 1 and 5, right? So if I think about that, I can go through and say, okay, it could be 5 here and 1 here. Does that work out? Well, the outer would be minus 9xy. The inner would be minus 5xy. Does that give me negative 46xy? No, it gives me negative 14xy, so that doesn't work. I can switch the order and put 5 here and 1 here. Now the outer would be negative 45xy. So negative 45xy, and the inner would be minus xy. If we sum these, we do get negative 46xy, so we don't even need to check this. We can get rid of that. So we've correctly factored this. We get 5 times the quantity 9x. You can just go ahead and say minus y times the quantity x minus 5y. In this lesson, we want to review special factoring. So a few lessons ago, we reviewed special polynomial products, or just special products for short. In that lesson, we looked at a few useful formulas that allowed us to quickly find the product of commonly occurring multiplication scenarios when working with binomials. So here we're going to use the same thought process, but for factoring instead of multiplication. So a lot of the formulas you're going to see in this lesson are just reversing what we've already seen. So if we start out with something like the difference of two squares, we've already seen the reverse of this. So if we have something like x squared minus y squared, this is equal to, so you take the first thing that's squared, so x is being squared, so that's going to go in the first position of each binomial. And then you take the second thing that's being squared, here it's y. Y is being squared, so that goes in the last position of each binomial, or the second position, and then you just have alternate signs. Now, in our lesson on special products, we saw this, right? We called it the product of conjugates, or we could say the product of the sum and difference of the same two terms. You have an x here and an x here, a y here and a y here, so it's the same two terms, it's just different signs. In other words, if we looked at something like x plus 5, this quantity multiplied by the quantity x minus 5, this matches our pattern, right? We have x and x, we have 5 and 5, and then different signs. What happens is, in the FOIL process, the o and the I are going to cancel, right? So the outer here is negative 5x, the inner here is 5x. So they will cancel, and you'll just be left with the first thing squared, in this case it's x, so x squared, minus the last guy, which is 5 squared. So 5 squared is 25. Now, if we want to reverse this, and we start out with x squared minus 25, how would we apply this formula here? The easiest thing to do is to write it in this format. So we know that x is squared. For emphasis, I'm just going to put x inside of parentheses. This is not illegal. This is not changing anything. This is just for emphasis. So x is being squared. Then minus. What is 25 in terms of taking the square root of it? In other words, square root of 25 is 5. So what's being squared there? 5 is. So I can write this as 5 squared. If you break things down into this format to where you can match this completely, you can easily recall your formula. Okay, you don't need to do this every time. As you get better with this, you're not going to have to do that. But when you first start, it makes it a little bit easier. So what's being squared here minus what's being squared here. So the first thing that's being squared goes in the first position of each binomial. So I'll put an x in the first position of each binomial because that's the first thing that's being squared. The last thing that's being squared, in this case it's a 5, goes in the last position of each binomial. Okay, very easy to remember. And then you just have alternating signs. So you have a plus and a minus, or you could flip that around and you could put a minus and a plus. Okay, very, very easy. Now, not all of them are so straightforward like this problem was. So let's think about something like 16x squared minus, let's say, 81y squared. So what we do here, again, I just want to think about what's being squared minus what's being squared. That will allow me to use my formula. Well, here I have not only a number or coefficient, I also have a variable. So 16 is a perfect square. 16 is 4 times 4. So I'm going to write this as 4x. This whole thing is being squared, right? Don't change this into just 4x squared because that would not be correct. These are not going to be equal because the 4 is not squared there. So you got to account for that and put this inside of some parentheses. So 4x is being squared minus the square root of 81 is 9. And we know y is being squared. So 9y, and this whole thing is being squared. Okay, so what's being squared minus what's being squared? Again, just follow the formula. So this is the first guy squared. So 4x is the first guy squared. So it goes in the first position of each binomial. Very, very easy. 9y is the second thing that's being squared. So it goes in the second position or the last position of each binomial. And you just alternate the signs. So plus and then minus, or you could do minus and then plus. Okay, very easy. So you get the quantity 4x plus 9y times the quantity 4x minus 9y. All right, let's take a look at another one. So we have 8x to the 10th power minus 50y to the 12th power. Now, if I look at 8, that's not a perfect square, right? And if I look at 50, that's also not a perfect square. That means that there's no rational number that I can multiply by itself to get to 8. There's no rational number that I can multiply by itself to get to 50. But 8 and 50 are each divisible by 2. Whenever you're factoring, you want to always think about, can I pull anything out before I start? In this case, I can pull out a 2, and I would be left with 4x to the 10th power minus 25y to the 12th power. Now, 4 is a perfect square, 25 is a perfect square. So now we know we can use our difference of two squares formula. I'm going to go ahead and write this first part, 4x to the 10th power has 2x. What does x need to be raised to here? Remember, it's going to be squared. So if it's something here and it's going to be squared, we use division. If it's 10, then we're going to end up with 10 divided by 2 would give me 5. Okay, so let me just change this to a 5. And then minus, we have this 25y to the 12th power. Square root of 25 is 5. And then, of course, I would divide 12 by 2 to get 6. So this would be y to the 6th power, and this is squared. So let me kind of write this a little bit better. Okay, so now we want to use our formula. Don't forget the 2 out in front, so that's just going to stay out in front. We're going to set up 2 binomials here. The first guy that's being squared is 2x to the 5th power. So that guy is going to go in the first position of each binomial. Then we're going to have this 5y to the 6th power. That's the last guy being squared. So that goes in the last position of each binomial. And then I just alternate my signs. So plus and then minus. So this guy is going to factor into 2 times the quantity 2x to the 5th power plus 5y to the 6th power times the quantity 2x to the 5th power minus 5y to the 6th power. All right, so now let's think about factoring a perfect square trinomial. So whenever you have a binomial squared, it turns into a perfect square trinomial. So the reason it's a perfect square trinomial, remember, a perfect square as a number is a number that when you take the square root of it, you get a rational number. Well, for a perfect square trinomial, when you factor it, it becomes a binomial squared, okay? So this is something like x squared plus 2xy plus y squared, which would factor into the quantity x plus y squared. And then the other version of this is x squared minus, okay, you have a minus 2xy plus y squared equals, you have the quantity x minus y, and this is squared. All right, so let's look at an example of this. And this is relatively straightforward to check. Essentially, the first thing you need to do, again, if you have something like x plus y, this quantity squared, this gives you x squared plus 2xy plus y squared. So if it's in this format here, this part would be squared, something squared, and this part would be something squared. Is 5 a perfect square? No, right? 5 is not a perfect square. There's no rational number that I can multiply by itself to give me 5. If I want 5, I'd have to do square root of 5 times square root of 5. Square root of 5 is an irrational number. Same thing goes for 125. So at this point, it looks like we can't use our formula, but we're wrong, right? The reason we're wrong is that, again, when you're factoring stuff, you always want to look for additional things to pull out. So this is a 5. This is divisible by 5. It ends in a 0. This is divisible by 5. It ends in a 5. So I could pull a 5 out here. Before I start, I'd have x squared plus 10x plus 25. And now if I look, this is something squared. This is something squared, right? I could really write this. Let me kind of move this down. I could really write this as 5 times, in parentheses for emphasis, I'm just going to put x being squared, plus I'm going to put 2 multiplied by, this guy right here, this 25, I'm going to write as 5 being squared. So 2 times 5 times x. In other words, 2 times what's being squared here, which is x, times what's being squared here, which is 5. And this does, in fact, give me the 10x. So this exactly matches this format here, so we can use that to factor. So following this pattern, it's whatever the first thing is squared plus whatever the last thing is squared. So that's inside of parentheses. So in this case, that's going to be x that's squared here and 5 that's squared here. And then we just square this binomial, okay? So this factors into 5 times the quantity x plus 5 squared. All right, let's take a look at another one. So we have 441x squared minus 504xy plus 144y squared. Now, these are numbers that we don't work with very often. So for myself, if I have 441, usually I'm going to have a calculator, so I'm just going to go square root of 441 and see if that ends up being a rational number. If you do that, you end up getting 21. So I could really write this as 21x, that amount being squared. But I do notice something here. I notice that I can pull something out. 4 plus 4 is 8, 8 plus 1 is 9. 5 plus 4 is 9, and 1 plus 4 is 5, 5 plus 4 is 9. If a number's digits sum to 9 is divisible by 9, so that means we can pull a 9 out before we even start. 441 divided by 9 would give me 49. So this would be 49x squared minus 504 divided by 9 would be 56. So 56xy. And plus 144 divided by 9 would be 16. So you'd have 16y squared. Close the parentheses. Now, there's nothing else we can pull out because this is 7 times 7. This is 7 times 8 or 7 times 2 cubed. And this is 2 to the 4th power. So nothing else that's common to everything. All right, so again, I want to think about, is this something squared? Is this something squared? Well, yeah. 49 is 7 times 7. So I could write this as 7x being squared. I'm going to put minus, forget about this term for a second, plus, is this something squared? Yeah, 16 is 4 squared, so 4y, this guy squared. So is this guy minus 2 times this guy, 7x, times this guy, 4y. 2 times 7 is 14, 14 times 4 is 56, and then you have x times y, so you get 56xy. So it matches what we're looking for. We have the minus here, so in our formula, we want the 9 out in front of some parentheses. So we have a minus inside. And we just want the first guy that's being squared, which is 7x, minus the last guy that's being squared, which is 4y. And this binomial is squared. Okay? So we factored this guy as 9 times the quantity 7x minus 4y. And this is squared. All right, let's think about the sum of cubes. And I want to just make a special note here. This, if I read the formula, is x cubed plus y cubed. And it factors into x plus y, this quantity, times x squared minus xy plus y squared. Now, this is not the same as what we looked at when we saw x plus y inside of parentheses cubed, okay? A lot of students make the mistake of thinking this is x cubed plus y cubed. That is wrong, okay? Wrong. You cannot distribute this. This is not multiplication, okay? If you have xy cubed like that with multiplication, this is x cubed, y cubed. Okay, that's where people get that from. But it doesn't work with addition, okay? When you have this, remember, we talked about this in special products, this becomes x cubed plus 3x squared y plus 3xy squared plus y cubed. So these two are not going to be the same, okay? So what we're talking about here is the sum of cubes. So in other words, I have something cubed plus something else cubed, and that's what we're looking at. So let's take a look at an example. So we have 8x cubed plus 27y cubed. So is it something cubed plus something else cubed? Yeah, 8 is 2 cubed. So I could write this as 2x, that's being cubed, plus 27 is 3 cubed. So 3y, that's being cubed. And then I can follow my formula. So let me write the formula down again for you. So if we have x cubed plus y cubed, this is going to factor into, you have x plus y to start, And then you also have x squared minus xy plus y squared. Okay, so this one is a little bit more difficult to remember, but definitely one that's going to be more beneficial for you. All right, so if I follow the pattern here, the x represents what's being cubed, the y represents what's being cubed. So what's being cubed here, it's 2x. So I'm going to start out by putting 2x plus 3y, just following the pattern. And then we have the guy that's being cubed, the first one squared. So square 2x, I would get 2 squared is 4, x squared is just x squared. Then minus, you have x times y. So this guy times this guy, 2 times 3 is 6, x times y is xy. And then plus, you have y, or whatever the last thing is that's being cubed, being squared. So 3y squared, 3 squared is 9, y squared is just y squared. So this factors into 2x plus 3y, this quantity, times the quantity 4x squared minus 6xy plus 9y squared. All right, so we have one more formula to cover. We now have the difference of cubes. So we have something cubed, x cubed, minus y cubed, something else cubed. This turns into x minus y times this other quantity here, x squared plus xy plus y squared. So the difference here is going to be in the sign, right? So here I have a minus, whereas with the sum of cubes I had a plus. And here I have a plus, whereas with the sum of cubes I had a minus. So the way I remember this is that the first one is the same and the second one is different, okay? That's how I remember it. The last term here is always going to be plus. Now let's look at an example. And let me go ahead and just write the formula down because I know we're going to need it. So x cubed minus y cubed is going to factor into, again, the first guy is the same. So I'm going to put x minus y. And then the second guy is going to be different. So I'm going to have x squared. It's going to be different, so it's going to be plus. You're going to have xy. And then you always have a plus here. You're going to have y squared. Okay, so not too bad. All right, so if we have 320x to the 6th power minus 1080y to the 12th power. So looking at these two numbers, 320 and 1080, neither is a perfect cube. But again, you always want to think about what can you pull out before you start. This guy right here, I know it's an even number, so I can definitely pull out a 2. It ends in a 0, so I can pull out a 10. This also ends in a 0, so I can pull out a 10. So really, I know this would be 32 times 10. Okay, and I know you could do this faster on a calculator, but just for the sake of completeness, let's just write this out. This is 108 times 10. Now, these are still even numbers. 32 is an even number, and so is 108. So 108 divided by 4 is 27. So this would be 27 times 4. And this guy right here would be 4 times 8. So in other words, I could pull a 40 out from each. If I pulled out a 40, this guy right here would be what? It would be 8, which is a perfect cube. And then we'd have x to the 6th power. And then minus this guy right here, if I pulled out a 40, I'd have 27, which is a perfect cube. And then y to the 12th power. Okay? So always look for what you can pull out. A lot of times when you're doing factoring practice or on a test, they've given you something that's not a perfect cube so that you say, oh, I can't use the formula, and you kind of move on. So let me erase this, and we'll put this is equal to. So what's being cubed here? So 8 is what? It's 2 cubed. And then what's my exponent going to be? Again, if I'm using the power to power rule, something here raised to the 3rd power would give me a 6 here. So something times something gives me 6. 6 divided by 3 would give me 2. So this is a 2. And then we have minus. Over here, 27. The cube root of that would be 3, right? 3 cubed is 27. And then for y to the 12th power, again, you're just going to divide. 12 divided by 3 is 4. So y to the 4th power, and this is cubed. All right, so now we're just going to follow our pattern. We kind of move this down. All right, so we're going to have 40 out in front, and then it's x minus y. So it's the first thing being cubed minus the last thing being cubed. So we're just going to have 2x squared minus 3y to the 4th power. And then times, you have the first thing that's being cubed, now it's squared. So 2x squared is squared. So I'm going to put this in parentheses so we don't make mistakes. So 2 squared is 4. X squared squared is x to the 4th power. So this is 4x to the 4th power. Then we're going to have plus xy. So that corresponds to what's being cubed times what's being cubed. So 2x squared times 3y to the 4th power. 2 times 3 is 6. And then x squared times y to the 4th power. Okay. And lastly, we have plus whatever's being cubed last, which is 3y to the 4th power, is going to be squared. Again, let's use some parentheses so we don't make a mistake. 3 squared is 9. Y to the 4th power squared is y to the 8th power. So y to the 8th power. Okay. So this guy is going to factor into 40 times the quantity 2x squared minus 3y to the 4th power times the quantity 4x to the 4th power plus 6x squared y to the 4th plus 9y to the 8th power. So a more difficult, a more challenging formula to remember, but something that's definitely worth it to put it on a Post-it, put it on a flashcard, look at it, use it when you're doing your homework, and just practice, 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 and it'll become second nature for you. In this lesson, we want to review factoring by substitution. So for most of you watching this, this is something you've done before. Basically, the idea here is that normally we work with trinomials, and we factor those into the product of two binomials. And the trinomials that we're working with have a degree of 2. In the scenarios we're going to look at today, this won't be the case, right? We're going to look at more complicated polynomials, or more specifically, more complicated trinomials. So when you come across these, you generally are going to be given problems that allow you to factor them using a little simple substitution technique. So to cover this, if we have something like x to the 4th power plus 2x squared plus 1, notice that this 4 here, the larger exponent, is double that of the 2, okay? Normally we're working with something like this. Let's say we had something like x squared plus 5x plus 6. We all know at this point this can easily be factored into what? This first term here would be x. This first term here would be x. So I need two integers that sum to 5 and give me a product of 6. That's 2 and 3. So plus 2 and plus 3. So very easy to factor. This is the typical scenario we're looking at. Notice that this 2 here is double that of the exponent of 1. This 4 here, again, is double that of the exponent of 2. So we have the same kind of format, the same pattern. And so when this occurs, we can just use a little substitution to make our factoring much easier. Okay, so the way we do the substitution technique is we let another variable, a lot of times you see u, you might see z, you might see q, pick whatever you want, it doesn't really matter. You're going to let that variable be equal to the variable raised to the smaller power. So in this case, the variable raised to the smaller power, we have x squared. So we're going to say, let's let u be equal to x squared. And I'm going to rewrite this in such a way that it's clear where we need to replace things. X to the 4th power is x squared squared. Then plus, we'd have 2x squared, then plus 1. So in other words, I'm going to take and replace everywhere we have an x squared with a u, okay, because u is equal to x squared. So down here, where we'd have x squared, I'm just going to put a u, and that's going to be squared. And then plus, we have 2x squared, so I'm going to put 2u. And then lastly, plus 1. So all I want to do is factor this guy, and it's pretty easy to do. I know the first term for each binomial would be a u, right? Because u times u would give me u squared. And then I just need two integers that sum to 2 and give me a product of 1. Well, the only possibility there is 1 and 1, right? 1 times 1 is 1. 1 plus 1 is 2, so that works out. So you get u plus 1 times u plus 1, or u plus 1, that quantity squared. Now you're not done, okay? Because you want this in terms of x, because this is the variable you started working with in your original trinomial. So all I have to do is go back and resubstitute. So since u is equal to x squared, I can essentially, let me kind of scooch this down. I can just write this as x squared, right? Just plug in an x squared for u, plus 1 times, you'd have x squared plus 1. Or of course you could write that as the quantity x squared plus 1 squared. Let's move this down because it's kind of in the way. And let's move this up. So we'll say this is equal to this, right? And you can check this. Let me kind of scooch these up. You can check these if you want. X squared times x squared would be x to the 4th power. So that would give me that. The outer would be plus x squared. The inner would be plus x squared. So x squared plus x squared is 2x squared. So that's where we get that middle term. And the last, we have 1 times 1, which would give us 1. So checking this with FOIL, we see we got the correct factorization. All right, let's look at another example. So suppose we saw 7x to the 5th power minus 62x cubed minus 9x. At this point, you have a 5 and you have a 3 and you have a first power. This is not the normal pattern, but again, when you look at things and you're trying to factor, always ask yourself the question, can I pull something out before I start? Okay, I can obviously pull out an x here, and that would give me a 7x to the 4th power minus a 62x squared minus a 9. Okay, now this matches the format I'm looking for. I have the 4th power and I have squared. So what I'm going to do now, I'm going to put x times, inside of parentheses I'll have 7x squared squared, I'm just doing this for emphasis, minus 62x squared minus 9. And so I'm going to highlight this, and I'm just going to say, again, let's let u be equal to x squared. Okay, so what I'm going to have is x times the quantity, 7u squared minus 62u minus 9. And I'm going to factor this. So let me erase this real quick. And I'll just write this off to the side. So let u be equal to x squared. All right, so to factor this inside, I'm going to go ahead and use the grouping method or the AC method. So give me two integers whose product is 7 times negative 9 or negative 63. So this is the product I'm looking for. And whose sum is negative 62. So that's the sum. Well, if I think about this combination here, really I'm going to be thinking immediately about negative 63 and positive 1, right? So negative 63 and positive 1. So I'm going to write this as 7u squared. I'm going to do minus 63u. I'm going to do plus u, or plus 1u, however you want to write that, and then minus 9, okay? And then I'm just going to factor this using grouping. So I'd have x times, from the first group here, the 7u squared minus 63u, I can pull out a 7u. That would leave me with u minus 9. From this group here, I'm just going to pull out a 1, and that would leave me with u minus 9. And so what's going to end up happening is I have a common binomial factor of u minus 9. So that's going to come out. So I would have x times the quantity, 7u plus 1, times the quantity u minus 9. Okay? So let me erase all of this. We don't need it anymore. So now I'm just going to do some back substituting. I'm going to put this as equal to, I have x times the quantity, 7 times, u is going to be x squared, plus 1, and then times, for u I'm going to have x squared, and then minus 9. Now, am I done? You might think that you're done, but you're not. You always want to look for opportunities to factor further. In this particular case, 7x squared plus 1, I can't do anything with that. Can't do anything with x, but x squared minus 9, what can I do there? That's the difference of squares, right? I have x, which is squared, minus basically 3 squared, right? 9 is 3 squared. So I can further factor x squared minus 9 as x plus 3, that quantity, times x minus 3. So we're going to erase this, and we're going to put the quantity x plus 3 times the quantity x minus 3, okay? And if you were to go through and do the multiplication here, you will end up with this 7x to the 5th power minus 62x cubed minus 9x. So very important that when you go through these problems, you look for additional factoring, because if you would have left this as x squared minus 9 here, instead of factoring it further, that would be considered wrong, right? Because it's not completely factored. All right, let's look at another one. So we have 9 times the quantity x minus 4 squared, plus 30 times the quantity x minus 4, and then plus 25. So this is another opportunity to use our substitution technique. Notice how we have this guy right here and this guy right here. This one is squared, and this one is basically raised to the 1st power. So if I let this binomial x minus 4 be equal to a variable like u, I can factor using substitution. I'll have 9u squared, right? Just plugging in a u where this is, plus 30u plus 25. Now, I'm going to factor this using the grouping method. So this will be equal to, I want two integers whose product is 9 times 25, or 225. So the product is 225, and whose sum is 30. So sum is 30. So 225, if I'm breaking that down, let me kind of get this out of the way real quick. Move this over here. 225, I know, is 1 times 225. That's not going to help me. It would be 3 times 75. but that's not going to work. It would be 5 times 45, but that's not going to work. We could also do 9 times 25, but that won't work. And of course, we could do 15 times 15, and that would work, right? 15 times 15 is 225. 15 plus 15 is 30. So we found the two integers that we need. So let's erase all this. And let's go ahead and write this as 9u squared plus 15u plus 15u plus 25. Okay? So now we can factor this using grouping. From the first group, I can pull out a 3u. And I would have a 3u plus a 5. From the second group, I can pull out a 5, and I would have a 3u plus a 5. So I've got this common binomial factor now that I can take out. So if I take that out, I would have 3u plus 5 times the quantity 3u plus 5. Basically, 3u plus 5, that quantity squared. So let's go ahead and erase all this. And what I'm going to do is I'm going to replace my u with my x minus 4. So I'm going to say this is equal to, you'll have 3 times x minus 4, make sure to use parentheses, then plus 5 times 3 times, again, inside of parentheses, x minus 4, and then plus 5. Okay? So let's see what we can do to simplify here. So 3 times x is 3x. 3 times negative 4 would be negative 12, and then you have plus 5. Over here, it's the same thing, right? So I just put 3x minus 12 plus 5. And of course, negative 12 plus 5 is negative 7. So this ends up being 3x minus 7, this quantity times 3x minus 7. Or you could say the quantity 3x minus 7 squared, right? Either way. All right, let's take a look at one more of these. So we have 8 times the quantity x plus y raised to the power of 2z, plus 6 times the quantity x plus y raised to the power of z, and then minus 9. So this one's slightly more challenging than the one we just saw. What makes it more challenging is you have a variable in your exponent. So this kind of trips students up just a little bit. So the idea here is still the same. We're looking for that pattern, right? We have this 2z here, and we might as well say this is 1z or just z, right? So this guy, the larger exponent, is double that of the smaller. 2z is double that of just z. So again, if we see this pattern, we can use our little substitution technique. Now, what am I going to let my variable be equal to? Let's let u be equal to what? Well, to make this crystal clear, I'm going to rewrite this. I'm going to put this as 8 times the quantity x plus y raised to the power of just z. Let me kind of scooch this down for a minute. And then I'm going to raise this to the power of 2. Okay? So I haven't done anything illegal. Power to power rule will put me right back to this, right? Because this is my base. It's x plus y, that quantity. So I would take this exponent here, which is z, and I would multiply it by this exponent here, which is 2, which would get me back to the 2z, which I have there. Okay, so I haven't done anything illegal. Then plus, we have 6 times the quantity x plus y. This is raised to the power of z, and then minus 9. So I'm going to take this guy right here, the whole thing, the x plus y, that quantity raised to the power of z, and that's what I'm going to let my variable u be equal to. Okay, so x plus y raised to the power of z. Okay? So I am going to have 8 multiplied by, take this whole thing and replace it with a u, and that guy's going to be squared. Then plus, I'm going to have 6, replace this with a u, and then just minus 9. Let me kind of scooch this out of the way so we have some room to work. And so now I'm just going to factor this guy. 8u squared plus 6u minus 9. I'm going to just use my grouping method because that's easiest for me. So I want a product of what? 8 times negative 9 is negative 72. So negative 72 is the product. And I want a sum of 6. So 6 as the sum. So two integers that have a product of negative 72 and that have a sum of 6. So again, I like to just work with positives and I work out the sign as I go. 1 and 72 wouldn't do anything for me. 36 and 2 wouldn't do anything. 24 and 3 would not do anything. 4 and 18 wouldn't do anything. But when I get to 6 and 12, I can make that work, right? I need a negative product and a positive sum. So what I'm going to do is I'm going to let the larger number in terms of absolute value be positive, the smaller number in terms of absolute value be negative. So I would want a plus 12 and a minus 6. So I'm going to use that to rewrite this guy. So I'd have 8u squared plus 12u minus 6u minus 9. Okay, so I can erase this. I don't need any information anymore. And now I'm just going to factor using grouping. So over here, I know that in the first group, I can pull out a 4u. So I pull out a 4u. That would leave me with a 2u plus a 3. Over here, I know I can pull out a negative 3. That would leave me with a 2u plus a 3. So we have a common binomial factor here of 2u plus 3. I'm going to go ahead and factor that guy out. So this is going to give me the quantity 2u plus 3 multiplied by the quantity 4u minus 3. Okay? So I'm not done. Let me kind of erase all this. I don't need it anymore. And let me kind of just slide this up a little bit. So all I'm going to do is wherever I see a u, I'm going to plug this guy back in. So I'm going to say this is equal to, let me kind of slide this out of the way. So inside of parentheses, we're going to have 2 multiplied by, in place of u, I'm going to put x plus y raised to the power of z. So this has to be inside of parentheses because 2 is multiplying the whole thing. So x plus y, again, this is raised to the power of z, and then plus 3. And then I have another set of parentheses, 4 multiplied by, again, the same thing, I'm plugging in for u. So x plus y, this guy raised to the power of z, and then minus 3. Now, let me erase all this. I don't need any of this anymore. This is going to be my answer, right? This is what this guy factors into. So if you start with 8 times the quantity x plus y raised to the power of 2z, plus 6 times the quantity x plus y raised to the power of z, minus 9, this would factor into, or give us an answer of, we have the quantity 2 times the quantity x plus y raised to the power of z plus 3, multiplied by this quantity 4 times the quantity x plus y raised to the power of z, then minus 3. You can't make this any simpler. You can't really do anything else. The reason is because the exponent here and here is a z, right? It's not a number where you can kind of do some other things. Z, we don't know what it is. It just represents some unknown. So this is as simple as we can make this.